Welcome to our discussion of limits at infinity and asymptotes. So the limit as x approaches infinity of f of x, or the limit as x approaches negative infinity of f of x, is called the end behavior of f of x. So we basically have two ways of writing end behavior. One is called the limit format, and the other is the format we use when we learned it in Algebra 2 for the SOLs. And let me just show you what that was. So this is the other way we write end behavior. They mean the same thing. So looking at this picture here of this cubic function, this one would have end behavior on the right approaching positive infinity. So the limit of f of x as x approaches positive infinity would be positive infinity. And on the left, the limit as x approaches negative infinity of f of x would be negative infinity. And if it was an even function, your end behavior on both sides would be the same, either up, up, or down, down. Looking at this picture here, we have a horizontal asymptote indicated by this line. So if the limit as x approaches either positive or negative infinity of your function is some real number L, then the line y is equal to L is called the horizontal asymptote of f of x. So when we talk about the end behavior of polynomials, the degree of the polynomial determines its end behavior. So if you have an even degreed polynomial, you're either going to be up, up if you have a positive coefficient of the leading term, or you're going to be down, down if you have a negative coefficient of the leading term. So if we have an odd power as our highest power of the polynomial, then you're going to get down, up end behavior if the coefficient of the leading term is positive, and you'll get up, down behavior if the leading term of the coefficient is negative. So next, let's talk about rational functions. Rational functions are ratios of two polynomials, one in the numerator and one in the denominator. So we have several possibilities here for end behavior. Case 1 is the limit as x approaches either positive or negative infinity is 0. So the degree of p of x, the numerator polynomial, would be less than the degree of the denominator polynomial. So in this picture over here, I have a degree 2 divided by a degree 3. You're going to get your polynomial on both ends flattening out at y is equal to 0. So we have a horizontal asymptote, y is equal to 0. So the next case for rationals is the limit as x approaches either positive or negative infinity is the ratio a over b. A is the coefficient of the leading term in your numerator. B is the coefficient of the leading term in your denominator. When we refer to leading term, it would be the term with the highest power. So you sometimes have to reorder your polynomial. So your leading term in the numerator is your highest degree term, your highest powered term, and the same thing for your denominators. So you can take a good look at the leading terms which govern the end behavior in a polynomial. So we said the degree of the numerator would have to equal the degree of the denominator in this case. So a over b is the ratio. In this case, it would be 3 over 2 of the coefficients. So that means that you're going to end up with a horizontal asymptote. Y is equal to a over b. Your end behavior is going to approach that real number, a over b, on both ends. The next case we'll talk about is the case when you have a slant asymptote. So this slanted line right here we call a slant asymptote. In this case, the limit as x approaches positive or negative infinity is going to be either positive or negative infinity, depending on your function. So your slant asymptote will be of the form y is equal to mx plus b, a linear equation. So you will have a slant asymptote when the degree of your numerator is 1 higher than the degree of the denominator. In this example here, I've got power 2 in the numerator, power 1 in the denominator. So I'm going to have a slant asymptote. So we can determine the equation of our slant asymptote using polynomial long division. So we divide the denominator into the numerator to determine our y is equal to mx plus b for our slant asymptote. And we're going to do an example like that. And the next case is also positive or negative infinity. The limit as you approach either positive or negative infinity is either positive or negative infinity. Okay, so this is the case where you have no slant asymptote. The degree of the numerator is more than 1 higher than the degree of the denominator. So notice in this example right here, I've got degree 5 over degree 2. So the degree of the numerator is 2 more than the degree of the denominator. If this is the case, depending on which polynomial you have in the numerator and the denominator, you're going to approach positive infinity or negative infinity, and it really depends on the rational function itself. So let's take a look at a few polynomials and determine their infinite limits at infinity or negative infinity. So the first one says the limit as x approaches positive infinity. So we have the case where the degree of the numerator is equal to the degree of the denominator. So this is the case where your limit is going to be the ratio of the coefficients. So your limit as x approaches infinity is 3/2. So we have a horizontal asymptote. Y is equal to 3/2. In the second case, if I look at my highest degree terms here, x is approaching positive infinity. Well, the degree of the numerator is 2, the degree of the denominator is 3, so I have the case where we're going to approach 0 on the left and the right. So we say the limit as x approaches infinity is 0, and we'll have a horizontal asymptote, y is equal to 0. Now in the next example, if I look at the leading terms here again, I'm approaching negative infinity. Notice that the degree on the numerator is 2 more than the degree of the denominator. So we're going to do something a little different here to make sure we understand what's going on. We're going to divide by the highest power in the denominator, which is 3. So I'm going to take all of my terms and divide by x to the 3rd power. So this is my numerator, and I have to do it to every term. This gives me a good way of comparing all of my terms to see which ones are going to affect my final outcome. Okay, so now that I've done that, I examine what I have. Let's reduce it. So this would be, the first term here would be 3x squared. This is going to be 2 over x squared. And this one's okay like that. This one's going to be 2. This is 8 over x squared. And 5 over x cubed. All right, so now we think about what happens to these terms over here with an x to a power in the denominator. As x approaches negative infinity, these these denominators here are going to get very, very large. So a small number divided by a very large number goes to 0. So all of these terms over here are going to become insignificant. We say they tend to 0. All right, so what we're left with is just this part here. So we can simplify this as the limit as x approaches negative infinity of 3/2 x squared. So if we think about what would happen to this x squared if we put negative infinity into it, well, it would be infinity times infinity, based conceptually a very large number squared, meaning it would be positive. So we're going to tend to infinity here, positive infinity, some very large number. So that's our limit. It approaches positive infinity. So we've got infinity, we've got a horizontal asymptote for B, and we've got a horizontal asymptote for A. So in this example, we have the case where we have the numerator 1 degree higher than the denominator, which means we're going to have a slant asymptote. So we want to divide by the denominator into the numerator. So we get x, so that would be 2x cubed minus 5x. We'll put a 0 here for a placeholder. So we have negative 12x squared. 7 plus 5 is 12. Bring down. All right, then we're going to divide by negative 6. So negative 12x squared plus 30. Subtract. So you get 12x minus 52. So this is our remainder here. All right, so what we're interested in is the quotient on top that we have there, not the remainder itself. We want this. All right, so our slant asymptote will be y is equal to x minus 6. So the limit as x approaches positive infinity of x minus 6 will give us our limit. So if you imagine x is a very large number and you subtract from it 6, which would be insignificant, you're going to get positive infinity. So that's as x approaches positive infinity. The limit as x approaches negative infinity would be negative infinity minus 6. The negative 6 is insignificant once again, but this time you're going to get negative infinity. So on the left end, your limit is negative infinity. On the right end, your limit is positive infinity. So in this example, we're going to look at how to find infinite limits of radical functions, functions containing radicals. So these are square root examples. So what we do is we divide by the highest power that's inside the radical. So if I look at this first one here, my highest power inside the radical is x squared. So I'm going to divide underneath the radical here by x squared. And then I think about the fact that if I'm dividing under the radical by x squared, then if I take that outside the radical, I'm dividing by the square root of x squared. All right, and that can have either a positive or a negative result. So remember, if we take the square root of a number, we could have had a negative or a positive that we squared under the radical. Now this is going to be significant depending on whether you're approaching positive infinity or negative infinity. So if you're approaching positive infinity, we're going to consider this case here where we had a positive x under the radical. So if I take my numerator, I've got 3x. I'm going to divide that by the positive square root of x squared. Right, that's just the same thing as dividing by x, right? All right, because we're talking about positive x's. So now let's simplify it. What we have under the radical, that's 1 plus 1 over x squared. Okay, so we can take the limit in this form here. So this is going to cancel here. This is going to tend to 0 and become insignificant as x becomes very large. So we end up with 3 in the numerator and the square root of 1 in the denominator. So our limit is just 3 as x approaches positive infinity. All right, so now let's look at the next one. So we've got that x squared under the radical, so I'm going to divide by something, but this time I need to divide by negative square root of x squared because I will have a negative result because of the fact that the square, let's think about this. Let me just try to make sure you understand this. I've got 2 negatives underneath here, which means the square root of that, if I take that out, is negative x. All right? So in this case, if I look underneath the radical first, I've got the square root of x squared over x squared and 1 over x squared. Now in the numerator, I'll have 4x divided by, we have to use that negative version because we're tending toward negative infinity, which means I had this case where I had 2 negatives squared under the radical. All right, so remember that can go unnoticed if you're not aware of the fact that squaring a negative will give you the same result. All right, so we have to think about that. So now I've got 4x divided by negative square root of x squared, which is negative x. So underneath the radical, I'll have 1. This will be 1. Now this part here will tend to 0 as x gets very large. So I have 1 minus 0, so it's just 1 under the radical here. So then I can cross out these x's right here, and I'll have 4 divided by negative 1. That's just negative 4 divided by 1. My result is negative 4. Okay, another one here. I've got a square root, so I'm going to use this approach again. So I'm going to divide in the numerator under the radical by my highest power of x. These are all under the radical. Once I'm outside the radical, I have to consider the case where I'm talking about negative x's. So I'm dividing by the negative square root of x squared this time, and I'm going to do it here as well. So that's the same thing if I simplify as 4 minus, let's just go ahead and, well, we can go ahead and write it out and then cross things out. So this is x divided by negative x minus 2 over square root of x squared is x. All right, so this reduces to, these are going to tend to 0 here, this one as well, as x gets very large. These are going to cancel here. I'll get negative 1. So in the numerator, I'll have the square root of 4. In the denominator, I'll have negative 1. Square root of 4 is 2. 2 divided by negative 1 is negative 2. So we got negative 2. So this is the technique that we use for determining the limits of functions with radicals in them as x approaches positive and negative infinity. So we have a couple more square root limits that I want to talk about. Now in D here, what we've got going on is something a little bit different. We've got an x to the first power minus an x to the 1/2 power plus 1. So really the driver in this denominator is the x to the first power because that power is larger than x to the 1/2 power. So let's take a look at what that would look like if I wrote 2x to the 1/2. And then this would be, of course, let me just put the 1 here so you can see what I'm doing. So I've got this. Now if I divide all my terms by the highest power of x in the denominator, I'll get 2x to the 1/2 divided by x to the 1. I'll get x to the 1, x to the 1, x to the 1/2 divided by x to the 1, 1 divided by x to the 1. All right, so you don't have to write those ones, but I just want to make sure this is clear. So now let's examine which terms become insignificant as x gets very large. So anything where you've got a higher power in the denominator is going to tend to 0 and become insignificant. So this one has a higher power in the denominator. This one has a higher power in the denominator. This one here will be 1. So you end up with a 0 in the numerator and a 1 in the denominator. So this limit is actually 0. And this last one here, I've got a square root of x squared plus 6x. So my highest power in this case under the radical is x squared. And I'm approaching negative infinity right here. So I have to think about the fact that I'm really going to be, now let's write this out. Let's not get ahead of ourselves. I'm dividing by x squared under the radical. But since I'm tending to negative infinity, I'm really going to have a negative x, not a positive x. So we're talking about negative square root of x squared that we have when we're approaching negative infinity, as opposed to positive square root of x squared when we're approaching positive infinity. So I'm dividing by negative square root of x squared outside the radical here as well. All right, so now let's simplify this sum. So I've got 1 plus 6 over x in the numerator under the radical. I've got 10 divided by negative x here. I've got 2 negatives here, so that's plus. And I've got 14x. Square root of x squared is x. Right, so this is going to tend to 0 right here. This is going to cancel. This is going to tend to 0 here. So I'm going to end up with the square root of 1 divided by positive 14, which would be 1 over 14. So my limit as x approaches negative infinity approaches 1 over 14. So I've got this asymptote. So whenever we end up approaching a real number at negative infinity and positive infinity, we've got asymptotic behavior. So we've got a horizontal asymptote out here at when x approaches negative infinity, and here we're approaching a horizontal asymptote of 0 as x approaches positive infinity, and then in the other square root problems, the same idea, horizontal asymptote of 3 as x approaches infinity, horizontal asymptote of negative 4 as x approaches negative infinity, and negative 2 as x approaches negative infinity. So these square root functions like this can do one thing on the negative side as we approach negative infinity, and then they might have a different value that you're approaching as you approach positive infinity. So they have that difference going on. You have to be careful with your signs. Okay, one more thing we want to talk about are what happens with exponentials as x approaches infinity. And we're going to look at these two examples here. So what we do know already is if you have a function such as 2 to the x or e to the x, as x gets very large, then my function's going to shoot up rapidly, exponentially we say. As x gets very small, so a very, let's say negative 100 perhaps. What if this was negative 100? As x approaches infinity, negative 100 is a pretty small negative number, or a large negative number, if you will. So that's the same thing as saying you have 2 to the 100 in the denominator. All right, so that means I've got a very small number. 1 divided by a huge number is an extremely small number. So that's why as we head out this way, we approach 0, but we never actually get there, and we don't become negative as x tends to negative infinity. All right, so we end up having asymptotic behavior on one end of the exponential function. One end of it will approach 0 depending on how your function looks. All right, so if I look at this function here in a, what I'm going to do is I'm going to rewrite it by putting anything with a negative exponent. I'm going to move it down to the bottom here. So I've got positive exponent, and then I've got negative exponent, puts it down in the bottom. So as x gets very large, then this will become an insignificant number approaching 0, and this will as well. So you end up with 7 to the x power over 7 to the x power, those two numbers being equal, you're approaching 1. So my limit as x approaches infinity is 1. On this next one here, we're approaching negative infinity. So when x is approaching negative infinity, we know that x is going to be negative. So that's going to change which terms become insignificant. So if x is a negative number, then 7 to the x is going to become your negative exponent right here. So let's think about that. So that would put this one being a negative number here, this one being a negative number here, and then this would become negative x, so that's going to become a positive number, and this one will as well. So we're actually thinking about 1 over 7 to the x minus 7 to the x over 1 over 7 to the x here plus 7 to the x. So now it's these two terms, these first terms, that become insignificant when x is negative, and the last two are the ones that grow large. So we end up with negative 7 to the x over 7 to the x. When we simplify, we've got this negative here. So that ends up being negative 1. All right, so the limit for this one is negative 1. So these are all the examples that we're going to do regarding finding slant and horizontal asymptotes. And this is going to help us with understanding how our graphs look. So go ahead and try the homework problems on this and let me know if you run into any problems.